All right, so this is our third lecture in this chapter on ideal gas mixtures. We've been into the study of moist air, where it's psychrometrics, where we have dry air as one component and water vapor as the second component. And the water vapor in the moist air mixture does behave as an ideal gas. That's been observed, quantified, checked, and so that's the way we treat it in these calculations, as an ideal gas. Last time we talked about the three temperatures: the temperature dry bulb, the temperature wet bulb, and the temperature dew point. And they're tricky, but you have a lot of experience with these temperatures, especially the dew point temperature. And when you know, if you have humid air and you cool it, you can get condensation. Or if you have humid air and it's exposed to a cold surface at the edge of a room or edge of a boundary or something like that, like a cold window pane, you can get condensate on that. Or the cold glass holding your favorite beverage on a hot, humid day, it can sweat, it can have condensate form. So anyway, you have a lot of experience with that. Also, our two humidities, we're interested in the relative humidity and this funny humidity ratio, omega. What were the SI units of this humidity ratio? It was kilogram of vapor per kilogram of dry air. It's actually dimensionless, but it's a number, typically like 0.01 or 0.008, something like that, which is how many kilograms of vapor in our moist air mixture per kilogram of dry air in that same moist air mixture. All right, and then we have to solve problems. When you're studying humid air, often you're studying the flow of humid air through devices, and so often an open system analysis. Let's start with an open system analysis where you have one inlet and one outlet. It's very, very common. So you have a control volume, and you have the flow of humid air coming in at 1 and going out at 2. And what you're going to have to do in the next couple pages, I'm going to develop it, you're going to have a dry air balance. I can do that on this page. It's pretty straightforward. Water balances for different conditions of what could happen in this control volume. Even though you only have one inlet and one outlet for the humid air, you could have a pipe coming in, bringing in some sort of mass flow rate of liquid water, and it might spray into the control volume. If you're spraying liquid water in there, what is it doing? It's humidifying the air. You're adding humidity. It's a humidifier. Not that common around here, but up north where they have 9 months of winter, they often have to humidify the indoor air in buildings, otherwise you get a lot of static charges, everything dries out in the building. People are uncomfortable, their skins are dry, so a lot of homes have humidifiers, as well as buildings have humidifiers in the central system of the home or building. Okay, the other, which is more common for us around here, is we have 9 months, if not 12 months of summer. Okay, so you have to have a coil that's nice and cold. Inside that coil could be a refrigerant that's evaporating. We call it an evaporator. And if you're passing hot, humid air over that evaporator and trying to cool it, you better have a drip pan to collect off the condensate and handle the liquid that's being removed. So you could have M dot liquid being removed in an air conditioning application. All right. Sometimes up north they'll have a boiler, and this fluid that's being introduced in a humidifier, sometimes they'll actually put in steam and blow steam right into it. Now, not in your homes typically. It's typically they spray in water and then they have to evaporate it. In the energy balance, that's taken into account. But in a commercial building, they may have steam available and just blow that in to make it warm, humid air. So when you add water in your water balance, adding can be a little more difficult because are you adding vapor, superheated vapor, saturated vapor? Are you adding a liquid? What temperature is a liquid? But it's a lot easier when you're condensing it and taking it out. Nobody condenses off of a cooling coil and then takes out vapor. No, you only take out liquid. See, it's a lot easier. And the other question is what's the temperature of this liquid going out? This temperature is very, very close to, and so everybody approximates it as the leaving air temperature going out at state 2. Again, I'll try and emphasize this. The temperature of the liquid coming in could be much colder, much warmer than the air. It could even be superheated vapor or saturated vapor being blown into a humidifier. A lot more challenging. Here, this is very, very common. It's pretty simple. It's liquid condensate going out at temperature T2, the air exiting temperature. All right, now let's talk about our air balance for this control volume. And you say, well, the mass flow rate of dry air coming in at state 1. Do I have any more ins of dry air? Nope, no more ins. So basically a balance is simply all the sum of the ins equal the sum of the outs. That's all we're doing. And then you say, well, there's only one out, mass flow rate of dry air going out. Is there any dry air going out with the liquid condensate or coming in with the liquid water? No. And so often they drop the subscript. And when you have one inlet, one outlet, you just have the mass flow rate of dry air is constant through the system. That's why engineers like to track mass flow rates of dry air. We know it's conserved by the air balance, the dry air balance. Okay, now let's go and do some water balances. So when you do a water balance, first of all, consider the case where there's no water being added or removed, and you still have a system. You have the inlet 1, outlet 2. So you say, what is the mass flow rate of the vapor coming in at 1? And I have no other inlet or outlet of water. It's only vapor coming in at 1. Hence, if there's only one removal, the mass flow rate of vapor going out at 2. Well, what is the relationship between the mass flow rate of vapor flowing in at 1 and the mass flow rate of dry air? Couldn't I multiply omega 1 times the mass flow rate of dry air, and doesn't that give me the mass flow rate of vapor coming in? Check your units. Well, again, were the units the mass flow rate of dry air? M dot dry, get the SI units. Kilograms of dry air per second, multiply that by omega, I forgot the units. Omega. Kilograms of vapor per kilogram of dry air. Kilogram of vapor per kilogram of moist air or kilograms of vapor per kilogram of dry air? Does it make a difference? No, it makes a difference. It's per kilogram of dry air. Hence, the kilograms of dry air cancel. And yes, that shows us the units are kilograms of vapor per second flowing in. Likewise, over here, you have the mass flow rate of dry air times omega 2. Can I cancel this on both sides? Sure. What did we conclude? Well, if you have no addition of water or removal of water, then what's constant? Omega. Yeah, it has to be constant. Now we'll consider the next case. So this is like case 1, now case 2, then case 3. The next case, water is being added. Well, again, what type of system would want to add water to your moist air stream? A humidifier. And so here is a M dot. Now, I'm just going to put LIQ / VAP. Now, that's a long subscript, isn't it? But I'm emphasizing it could be liquid or it could be vapor. You've got to pay attention, especially when you get to the energy balance, because they have a lot different enthalpies. If I bring in liquid, it has a low enthalpy. If I bring in vapor, it has a high enthalpy. So, long subscript on that M dot, but that's just to help you. So we say, what's an in? The mass flow rate of dry air times omega 1 coming in. Isn't that my mass flow rate of vapor coming in? Yeah. Plus the mass flow rate of either liquid or vapor, whatever is being used to humidify the air, equal to the mass flow rate of dry air times omega 2. Is that a good water balance in your opinion? The 2 ins equal to the 1 out. Make sense? Good. Now you can rearrange that and you say, well, the mass flow rate of the liquid or vapor coming in is equal to the mass flow rate of the dry air times omega 2 minus omega 1. If I'm adding water, the humidity ratio needs to go up. Omega 2 better be greater than omega 1. Make sense? All right. I really don't even need to write the third equation, but let's do it anyway. Let's say we don't have humidification. We have our cooling coil, air conditioning application. We have our condensate pan to collect it, and we're coming out with m dot, and I'm just going to say it's liquid. We don't come out off the condensate drip pan anything but liquid. All right, we come in with state 1. We go out state 2 of our humid air, our little control volume, and so what's our in is our m dot of the dry air times omega 1. What's an out? Our m dot of the liquid is an out in this case, and we have the m dot of the dry air times the outlet humidity omega 2. Let's rewrite it. So the mass flow rate of the liquid condensate going out is the product of the dry air flow rate times the inlet higher humidity ratio minus the exit lower humidity ratio. Omega 1, if you're dehumidifying the air by passing it over a cooling coil, omega 1 is high on the inlet, omega 2 is lower on the outlet. Make sense? Well, once you have the easy one, the air balance, that was only one equation, simple. Then we go to the water balance, and I broke it down into 3 cases, the first being almost too trivial, but the other being humidification, then the dehumidification. Now we go to the energy balance. Energy balance. So, okay, energy balance with no water added or removed. So again, here's my control volume, and here's inlet state 1 and outlet state 2. Well, isn't it going to be the energy ins match the outs? Yeah. Okay, what would be my energy ins? It would be with the mass flow rate coming in. All right, mass flow rate coming in, but I have a mixture, 2 components. One is dry air and one is water vapor. So let me say it's a sum of 2 things. One is the dry air times the enthalpy of the dry air coming in. One is the mass flow rate of the water vapor coming in times the enthalpy of the water vapor coming in. Let's say there's no more heat addition. Well, if somebody said, well, what happens if I have a heating coil and I'm dumping Q dot in? Okay, well then add Q dot there. But I'm not bringing in heat or removing heat with any water added for humidity or removed with condensate, dehumidification. Okay, that would be all of my ins. Let's continue on. What about an out? Well, the mass flow rate of dry air with its enthalpy of the dry air going out. When would these 2 enthalpies of dry air be different? When the temperature is different. If maybe you heated it up, maybe the temperature at state 2 is high on the exit. Its enthalpy would be high on the exit. So, okay, let's continue on. And then we're going to have the mass flow rate of the mass flow rate of the vapor times exiting times the enthalpy of the vapor exiting. Does that make sense? Okay, I could replace the mass flow rate dry air times the enthalpy dry air 1 plus omega enthalpy of the vapor at 1. Here we put H of G at 1. What do you mean by H of G? Remember in Thermo 1 we had that subscript G for saturated vapor. And in the book there's a little discussion says, look at the vapor's enthalpy is essentially the saturated vapor enthalpy at that dry bulb temperature. So H of G, you look up at T1, and that's the vapor's enthalpy coming in. Okay. keep the Q dot there, equal to the mass flow rate of dry air times the enthalpy of dry air exiting at state 2 plus omega, I should put omega 1, omega 2 here, and then H of G2. All right. Yes, sir.
So you said that H sub B and H sub G are the same?
Yeah. The enthalpy of the water vapor is, to a very good approximation, the enthalpy of saturated saturated vapor at that dry bulb temperature.
Yeah, just from the table. Oh.
Yeah, straight out of the table. Okay. All right. Now, let's take a look at a couple of these. Professor, you didn't put a subscript on this m dot of dry air and that m dot of dry air. Are they the same? Yes. Why are they the same again? Only one inlet, one outlet, steady state. You don't condense dry air. You know, it's nitrogen, oxygen. It's conserved. Okay. How about these humidities? First, you didn't have a subscript on this one, and then you decided to add it, and omega 1, omega 2. Are they the same if no water is added or removed? They are the same. They're the same if no water is added or removed. All right. Sometimes what they'll do is they'll introduce just an H for the mixture. What? What do you mean by H of the mixture? It's an enthalpy for the moist air. It's the enthalpy of the dry air plus the omega times the enthalpy of saturated vapor. The enthalpy of dry air is evaluated at that temperature dry bulb, as well as H of G is evaluated at the temperature dry bulb, whatever the dry bulb temperature, in or out. You could rewrite this equation as Q dot divided by m dot of the dry air is equal to the exit mixture enthalpy minus the inlet mixture enthalpy. Let me try and write it a couple ways here. This would be equal to enthalpy of the dry air on the exit, enthalpy exit minus enthalpy inlet of the dry air, plus, we said the omegas, the humidity ratio, doesn't change, times H of G2 minus H of G1. And then you could say, well, this is specific heat constant pressure of the dry air times the temperature change. Absolutely true. Absolutely true. And this is just humidity ratio times, you could put in, and I've seen some people do it, they'll go get a specific heat for the water vapor in that temperature range, and then multiply that by a delta T, T2 minus T1. You could do that too. But what I'm going to emphasize right here is this is the amount of heat needed per unit mass flow rate of this Q dot divided by m dot. This is to heat up the dry air that goes into heating the dry air. What is this? This is how much heat, what you could do a percent. You could say, oh, 90% of the heat added goes to heating up the dry air, 10% goes to heating up the water vapor, changing the water vapor's temperature. Both of those are realized by a change in the temperature. Both of those are what they call sensible heating. Sensible heat of the dry air, sensible heat of the water vapor. All right, we're only going to get more complicated. You ready to go? All right. Well, let's do this one. Let's do the cooling application where you're going to remove the liquid condensate. So again, let's draw a little control volume. We're coming in with the humid air stream at 1, going out humid air stream at 2. We're going to have a little drip pan. We're going to come out with the mass flow rate of the liquid coming out. And we know that liquid is coming out at enthalpy of saturated liquid at the temperature T2. All right. Now, the way it worked was you had a cold refrigerant coil there. Either what they call a DX coil because it's direct expansion inside the tubes is a refrigerant that's evaporating, common, or even just as common in big commercial applications, it's water, cold water, chilled water inside the tubes. But anyway, from the perspective of the energy for the moist air, there's a Q dot, get rid of this red line there, Q dot going out. Going out of what? Going out of the moist air stream. Where is it going? Either into the refrigerant that's inside the coil or the water that's inside the coil, but it's going out. Makes sense? Now we'll do our energy balance. So this is a air conditioning summer application. Okay. So we're going to have, depends how you want to do this. Let's go slow. M dot dry air times the enthalpy of the dry air coming in plus omega 1 times the M dot dry air times the H of G1. All right, that's all coming in with that fluid stream. Are there any other ins for the rate of energy transfer into the control volume? No. We have an out in the form of heat transfer. We have an out in the form of the dry air flowing out, enthalpy dry air at 2, taking with it the omega 1 Hg 2, that's 2. Okay, I didn't leave enough room, did I? I have to scoot that down. I'm going to scoot this down a little bit. Sorry about that. Okay. And then I have another out, which is the mass flow rate of the liquid times the enthalpy of the saturated liquid at the temperature T2. I pause for a minute. Did I make a sign error anywhere? Do you like it? Can you give me a thumbs up or correct me if you see an error? Is it okay? All right, couple questions. Is this M dot dry air the same as this M dot dry air? Yes, it is, because we have only one inlet, one outlet. In this case, is omega 1 equal to omega 2? No, it's not. Why? Got liquid water going out. All right, so we have already done the water balance, and we found that the mass flow rate of the liquid going out is the mass flow rate of the dry air going through times omega 1 minus omega 2. I'm going to pause right there. Either look in your notes or just give me a thumbs up if you agree with this equation. Where did this equation come from? This is a water balance equation. What we're going to substitute right there, aren't we? All right. So let's continue to do this. Let me do it like this. I'm going to put Q dot divided by the mass flow rate of the dry air is equal to enthalpy dry air inlet minus enthalpy dry air exit plus omega 1 times the Hg inlet minus minus omega 2 Hg outlet. And then I'm going to have omega 1 minus omega 2 times HF. I'm going to say HF at 2, something like that. But okay, at T2. All right, I'm going to pause right there. I did some algebra and I wanted to not do too many steps. Did I do okay? 1 thumbs up. 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10. Thank you very much. 11. Thank you. All right. Last time I made an error. I think I put a plus sign right there. But this time I think I kept the signs correct. I think it's okay. Now, with this equation, what I'm going to do is I'm going to scoot H of G over here. All right? And I'm going to put a parenthesis like that. And I'm going to put a minus W2 and a plus W2. Or omega, I should say omega instead of W, right? It's a Greek letter. Did I change the equation any? No, I just added the 0. Okay? But why did we do that? Well, because I can group this term with that term right there. So let me do this. Let me rewrite this. Also, I'm going to introduce the C sub P of dry air, and then this is T1 minus T2. Isn't that right for that first term? Okay. Then I'm going to have omega 2 times Hg1 minus Hg2. That's the two red underlined terms. And then we can combine, and we'll have omega 1 minus omega 2 times Hg1 minus Hf going out at T2. What I want to do is now interpret this. Whenever you see something like this, that's the sensible heat of the dry air. It's like, oh, that's a sensible heating of the dry air. Okay, what is this? Well, omega, if you're having liquid condensate removed, which one's larger? Omega 1 is larger, isn't it? This is larger. This is smaller, omega 2. What does omega 2 represent? It represents the vapor that started in the inlet stream and exited at the exit stream. It was vapor the whole time. So this is the sensible cooling, I should say not heating, I should say cooling. Sensible cooling of the vapor that stayed vapor. It didn't condense. All right. What is this term? Well, it came in Hg. What did it went out as? HF. It went in vapor, came out liquid. So this is what they call the latent load. Latent cooling load. Let's do that. All right, what do they mean by sensible and latent? There's the old terms, they go back. Sensible means, oh, because I either added heat or removed heat, there was a proportional temperature change. That makes sense to us. And typically the proportionality constant is specific heat. All right. What about latent? Latent, go back to etymology, study of the word, is something about hidden. It doesn't really make sense because even though I put heat into something, it didn't change its temperature. It kind of hid the heat by not changing the temperature of the substance. Often that's associated with vaporization. Or if I remove the heat transfer out. If it's latent, it don't make sense because it didn't change the temperature. It just changed the phase. See? So this is the cooling load, which is due to the condensation primarily. I know there's a little bit of subcooling or going the vapor Hg1 to Hg2, but I'm not going to worry about that. It's just primarily the HFG. All right. Because these are at slightly different temperatures. This is at temperature T1, and that's H of F at temperature T2. All right, hopefully all that made sense. Because this is a big deal. How much energy you require to run your air conditioner in the middle of summer in your house to keep your house cool. There's a lot of energy just to dehumidify that air. The air conditioner is dehumidifying air a lot of times, wringing the moisture out. You can watch it drip off the condensate line, either a room window air unit or a central unit. Okay, one other thing is I need to talk about this mixture enthalpy. If sometimes it's convenient to just say, hey, I'm going to have the moist air mixture enthalpy as the enthalpy from the dry air plus the humidity ratio times the enthalpy of the vapor in the air. And when you want to evaluate that, typically you go to the tables to pick up this H of G. Maybe you need it H of G at 30 degrees C or 22 degrees C, etc. But then somewhere in this textbook, I know it's embedded in a problem, I wish they'd have put it in the chapter, is a very good approximation. And it's in all HVAC textbooks, can't spell today, sorry. Any book studying heating, ventilation, air conditioning will have this nice approximation for H. So they put C sub P times the temperature, but that temperature needs to be in degrees C, not in Kelvin, not in Fahrenheit, nothing, degrees C, plus omega times 2501.7 plus 1.82 times this temperature must be in degrees C, close paren. So both of these temperatures that you put right here are in degrees C, and this will give you a very good H for the mixture. And it accounts for not only dry air enthalpy, but also the water vapor enthalpy. All right. Yes, sir.
Where do the units degrees C go?
That's a lot of times just what happens in engineering. If you wanted to, you could work out that this C sub P has the kilojoules per kilogram degrees C. No problem. But over here, this is dimensionless, this omega, or you could put your kilograms of vapor per kilogram of dry air. And then you say, okay, well, what does this have to have for units? It has to have units of like kilojoules per kilogram of vapor. And then this, when you say, okay, what's that have to have? That 1.82 has to have something like kilojoules per kilogram of vapor per degree C. And then your degrees C's cancel when you multiply by temperature in degrees C. But I tried to explain this before. I get a lot of questions about these type of things. It's all where you start your energy reference. And for this equation, if I put in a temperature of 0 degrees C, what is my mixture enthalpy? Is some crazy on this term, and that's about it. But from the point of perspective of the air, it's 0. And you go to the table, appendix, let's say, what is the air table? Don't go there. Do not avoid the air table with this equation, because when you run that number and you compare it with the psychrometric chart, which we're going to get to and you need to use for homework, that you'll be off by numbers. And you'll be like, wow, this doesn't make sense. How come it's really crazily different? Well, because this equation, and especially this rendition of it, resets or calibrates it such that at temperature is 0, the enthalpy of dry air is 0. Or if you want, do this. If you want to really use the air table, you can do that. It's just when you're talking about the enthalpy of dry air, do this. Put in the enthalpy at that temperature, but minus the enthalpy from the same table at 273 Kelvin, and it'll work. I don't know if I'm getting through. That's a more challenging concept than other stuff that I'm talking about today. But let's press forward. This is a great approximation. It saves you from having to go into the tables, especially if you need to guess and iterate. A lot of times having analytic expression for this mixture enthalpy allows you to say, oh, wow, now I can manipulate and solve for the temperature or the humidity ratio right away. Moist air at 25 C, 101 kilopascal, 75% relative humidity, flows over a cooling coil. The volumetric flow rate entering is 130 meter cube per minute. Air leaves at a lower temperature, same pressure, and higher relative humidity. So make a nice schematic. And you might as well put in here that you have a coil, might as well color code it blue, indicating it's cold. And as the air flows over it, there's going to be a rate of heat transfer, Q dot, out of the moist air to the fluid in the coil. And so this is coming in at state 1, going out at state 2, and we better put a drip pan, and we have the mass flow rate of the liquid condensate. Okay. What is the mass flow rate of the dry air? And there's the answer. Well, they give me the volumetric flow rate, AV, coming in at 1. That's 130 meter cube per minute. I would like to calculate the mass flow rate of the dry air being the volumetric flow rate of the air, total volumetric flow rate of the air, times the density of the dry air coming in at 1. All right, the density of the dry air coming in at 1 using the ideal gas equation is the pressure of the dry air coming in at 1 times the molar mass of the dry air divided by R bar T1. Hey, where did that equation come from? Ideal gas. What is the partial pressure of the dry air coming in at 1? The total pressure at 1 minus the vapor pressure at 1. What's the vapor pressure at 1? I need to know the relative humidity at 1 and the saturation pressure at 1 at the T1. So finally, it's like, okay, I can break this down to a number of steps. Once you've done this a few times, you get into the rhythm. Go to the table and get the saturation pressure at a temperature of 25, excuse me. All right, so the saturation pressure would be 3.169 kPa, such that the vapor pressure, it's 75% relative humidity, and so that becomes 2.377 kPa. Then the dry air pressure is 98.92 kPa. Hey, Professor, if I just put in the 101.325, whatever, would that have been such a big error? Well, no, not really. It would not be that big of a numerical error, but it's conceptually an error. So you want to, the P1 is close to P dry air at 1, but it's not exactly the same. Okay. And then we get the density. I don't know if I have a separate value for it, but once I have the density, then I multiply and I get the mass flow rate. The mass flow rate comes in 2.506 kilograms per second. If I round it off to 3 digits, 2.51 kilograms per second. Because the temperature really is how many digits on this temperature? All right. What about the condensate flow rate leaving the coil? That's this term, the mass flow rate of the liquid. Well, the mass from a water balance, the mass flow rate of the liquid is equal to the mass flow rate of the dry air, which we just calculated for part A, times omega 1 minus omega 2. Isn't it? Yeah, so it's a water balance. How do I calculate omega 1? 0.622. The pressure of the vapor at state 1, the pressure of dry air at state 1. And those numbers, let me see, 0.014944. Too many digits, I know, but keep them. Omega 2, 0.622. I have to get the vapor pressure at 2. How do I do that? Well, a little bit of work, just like these calculations right here. I got to get the Psat at the temperature 2, multiply it by the relative humidity at 2, then I have PV at 2, and then I need to also calculate the pressure of the dry air at state 2, just like this equation. And this is a 0.008287. It's decreased, which is good. And then it allows me to calculate the final condensate flow rate. You got to watch kilograms per second versus kilograms per minute. Okay. What is the rate of heat transfer to the coil? Are you sure it's not from the coil? No, it's to the coil. Remember, it's the coil is cooling the air. So it's coming out of the air and going to the coil. That's the direction of the heat transfer. All right, well, you go back and you go, well, Q dot equal to the mass flow rate of the dry air. And then we have, you can do it a couple ways. The last equation that I showed was a specific heat of the dry air, then the temperature exit minus temperature inlet, dry bulb temperatures for the dry air. And then we had, what was the omega, the humidity ratio that it was exiting. We think, oh, that's what came in and went out, stayed in the vapor state. And then we're going to have h of g at 2, state 2, minus h of g at 1. Then the other one, both of these are my sensible cooling of the dry air, sensible cooling of the vapor that stays vapor. And then I have the third term, the latent. The latent is you have your omega 1 minus omega 2 times, I didn't leave enough room, hg1 minus hf at the temperature T2. That all goes right there. We wrote those equations earlier. Yes, sir.
Does it matter the orientation of the T's and the HGs, or are you just going to get assigned different?
Well, this is a removal, and so this T2 is higher, this Hg2 is higher, and this Hg1 is higher. So all of these are positive enthalpy changes, positive enthalpy change, positive temperature change. Is there a sign error that I have, or is it okay?
Well, just when you had it written down on the previous page, you had it as the T1 minus T2. So we were just writing it.
Oh, I have a typo on the previous page.
I don't know.
This page? Oh, look at that. Hold it. I messed up then. I'm sorry. This is coming in at a higher temperature, leaving at a lower temperature. Coming in at a higher enthalpy of the vapor, going out at a lower enthalpy of the vapor. Hot coming in at a higher vapor enthalpy, going out. Okay, thank you very much. I think he helped fix my error. True?
5 points.
5 points.
On the final.
You have a generous neighbor. All right, so thank you very much. Okay, I think when I run the numbers, this comes in to be like 32.7 kilowatts, 0.49 kilowatts, and 41.66 kilowatts, giving a total of 74.84 kilowatts. Okay, a little different. I reran it. But it basically is 44% of the cooling load is due to the sensible cooling of the dry air. 0.7, come on, we're engineers. Negligible. Sensible cooling of the vapor that stays vapor. But a whopping over 50%, 55% is due to latent load on that coil, meaning you're condensing water. All right? You're removing humidity as you condense it. All right. Here is work that out on Excel sheet. One thing that I wanted to point out was I did calculate the mixture enthalpy in kilojoules per kilogram of dry air. Here's a number for state 1. Here's a number for state 2. When I use the simple approximation, there's that repeated approximation. Compare at state 1, almost good to 4 significant digits, that simple approximation, versus going into the tables and doing interpolation. And likewise here, that's very good. All right? So again, this is a nice approximation that I recommend that you use. I asked people at 8:30 class if that was in the equation sheet. I think they said no. They said, but would you put it up on the chalkboard during the test, next test? I said, okay, no problem. So I'll put that one up. So if you know how to use it, maybe it saves you a little time. All right? All right. Well, what happens when you have 2 inlets and 1 outlet? Well, typically this is just mixing, isn't it? So you have just 1, and then 1, and then 1, like that. And so we come in with state 1, we do inlet state 2, and we go out with state 3. All right. If you just have mixing, a lot of times Q dot is equal to 0. There's no heat transfer, no cooling. All right. There's no m dot liquid removed or vapor added. You're not humidifying or dehumidifying. You're just mixing two moist air streams. All right, if you do an air balance, you get that the mass flow rate of the dry air coming in at 1 plus the mass flow rate of the dry air coming in stream 2 is equal to the mass flow rate dry air going out at stream 3. Pretty good. Do a water balance. All right. That means the humidity ratio in times m dot dry air 1 plus humidity ratio 2 times m dot dry air 2 equal to humidity ratio 3 m dot dry air 3. Does that look reasonable? Well, the rate of flow in with stream 1 of the vapor plus the inlet flow rate from stream 2, and that mixes and goes out as 3. All right. How about the energy balance? Well, let's go ahead and use the mixture enthalpy coming in at 1 times the mass flow rate of dry air at 1 plus the mixture enthalpy at 2, mass flow rate dry air at 2 equal to the mixture enthalpy at 3, the enthalpy, the mass flow rate dry air 3. And then you've seen this pattern a lot in engineering. And you say, well, a lot of times, it's like givens and given, and you're asked to find what the conditions are on the outlet. Well, if you're asked to find what omega 3 is, wouldn't it be omega 1 times the m dot dA1 plus omega 2 times m dot dA2 divided by m dot dA1 plus m dot dA2? And then you look at it and like, this is a fraction. And that's another fraction. It's simply a weighted average. So if I had a straight line and I said, hey, this was omega 1 and this was omega 2, and I said it's 50-50, I would take the length of the straight line between them, cut it in half, and there would be omega 3. What do you mean by 50-50? If the m dot dry air 1 divided by the sum of 1 and 2 was 0.5 and the other fraction was 0.5, it'd be 50-50. What happens if somebody says, oh no, this ratio is 0.9, hence this ratio in red is 0.1? Well, you have a straight line, and you would divide it and do 90% and 10% of the straight line, and it would be way over here, right? It would be like this length of the line would be 0.1 and this length of the line 0.9. We're preparing you for the psychrometric chart. Yeah, we put a straight line on the psychrometric chart, and we say, oh, look at that, it's a ratio, a mixing, and it's 90%, 10%, or 50%, 60%, whatever. Look at the energy equation. Somebody says, what is H3? It's H1 times some fraction plus H2 times the other percent of the fraction. And what's the ratio? It's the mass flow rate of the dry air 1 divided by mass flow rate dry air 1 plus mass flow rate dry air 2. See that ratio right there. And then the other ratio is mass flow rate dry air 2. Go like that. So you have two enthalpies. You do a straight line, and then it's whatever the percent of the length of the line is the mass flow rate fraction. All right. Well, there's a lot of problems to solve. Please solve a lot of problems. I need to talk about the psychrometric chart. One of the last big topics. You can find your psychrometric charts where? At the back of the figures in the appendix. We only are going to be interested in the SI, but if you go out and work in this industry, the HVAC industry, be prepared for USCS, BTUs and feet, etc. Let's move on. This is the psychrometric chart. It looks a little daunting, but it's just an XY plot with a bunch of lines on it. On the X, you have the dry bulb temperature. It starts at -10 and it goes up to 50. This is really, really cold, and this is really, really hot. Most of the time, you're in this range of 10, 20, 30-ish in that vicinity for the dry bulb temperature. But they kind of push the boundaries. The other thing I forgot to emphasize, these charts that are in the appendix are good for 1 ATM. Corpus Christi, Houston, congratulations. You go work in Denver, Mile High, get a different chart. Don't use the 1 ATM. They have them for high altitudes, but it changes because the total gas pressure is different. A little warning there, but oh, by the way, they have these all in computer codes now anyway. So that they can have a computer-generated psychrometric chart for your application at your elevation, whatever. Okay. Now, what about the y-axis? Well, most of the time they put the y-axis over here on the left, but there's nothing to say you can't put it on the right. True? Yeah, so they put it on the right side. The y-axis is my humidity ratio, my omega. Look at the units, kilograms of water per kilogram of dry air. They remind us. Good, just like the degree C for the dry bulb. Now we want to find relative humidity lines. These are the lines that go like this. That's a 10% relative humidity. This is a 20%. There's a 30. A lot of times we work with the 50% relative humidity line. It's a very special line, 50%. We like to keep the indoor conditions in this building right now, this room. The target for the engineer would be about 72 degrees F, 50% relative humidity. That would be the target. It starts pushing 60% humidity, people can feel it. Starts pushing 40%, people can feel it. So 50% is the target. If you get 70 or 80%, there are going to be phone calls to every, technician on campus. Get over here and fix it. We are super uncomfortable. Or if it gets really dry. Okay, anyway. 50% relative humidity. And then you keep going. What's this last line way up here? 100%. What's above this line? No man's land. You don't have water, moist air in equilibrium at 10 degrees C at 0.0022 humidity ratio. It doesn't exist. It would be super saturated. It would have condensed. The best you can do if you're at 10 degrees C is be at this omega, and it's saturated. It's 100% relative humidity. Or if you're at this temperature, 30 degrees C, well, yeah, it can hold a lot more. You can get a really high omega. You can get a lot of kilograms of water per kilogram of dry air. But you can't have a point out in here. It doesn't make sense, so there's the maximum. That's why they put the y-axis on the right. Okay, let's keep going. What about the dew point? Pick a temperature. It's easiest to describe or find the dew point. So let's say we're at 25 degrees C, and we're at 50% relative humidity. Right there is the condition in this room, hypothetically. It's a little cooler, maybe. Okay. Somebody says, what's the dew point temperature for that point? When my dry bulb's 25 and my relative humidity is 50%. Play a game conceptually where you just cool it without dehumidifying. If you humidified, you'd go up with omega. You would go down if you dehumidified. If you stayed along a line of constant omega, are you changing the humidity? No. You're not condensing, or you're not adding water vapor to the mixture. So you just play a game of cooling it at constant omega. Now, if I move to this point right here, my dry bulb is dropped. Maybe it's 19 degrees C. Relative humidity is 70%. See how I'm conceptually playing that game? And you keep going until you hit the wall, until you hit the end. Now I'm at 100% relative humidity. If I try to cool it some more, I can't do it without dropping omega, meaning I'm doing it out now. I've hit the dew point. I can't, this is that temperature right here, it looks like it's around 14 degrees C, is my dew point temperature for the air in this room. Now what about the wet bulb? Well, the wet bulb is like a line of constant enthalpy. Some of them have slightly different slopes to them, but I'm just going to say you just go along this slope right here. All right? That slope, you go up. It's like a constant enthalpy. These are different enthalpies out here, mixture enthalpies. And then you find this point right here, and then you say, what is the temperature? Well, sometimes it's between 20 and 10. You can interpolate along that line, or you just drop it down and it looks like it's around 18. So the wet bulb in this room would be around 18 degrees C. What was a dry bulb? 25 degrees C, and relative humidity is 50%. Okay. Then what about the specific volume? Well, these are lines here. I should change color or something to make it more entertaining. I don't know. These are lines of constant specific volume. See that? And they have the units right in here. Hopefully you can read that. So if I was right here, it would be, okay, this is 0.80. This is 0.85. I'm covering up the numbers, aren't I? 0.85, right? This is 0.90. This is a line right here. It seems to go right through that point. What is my specific volume? 0.86. What are the units? Meter cubed per kilogram of dry air. Reciprocate that, and I have the density of dry air. Okay. The last one is my mixture enthalpy. Just go along that line. You can take a straight edge and project these lines. That's why they give them to you, so that you can project it back nicely. And you can do pretty good with the straight edge. And you would see that, oh, this looks like it's around, I don't know, what is that? You read that for me. 51? Okay, 50, 51, somewhere in there. What units? Kilojoules per kilogram of dry air. There's a lot of information. If you take an HVAC class, they have a little like protractor up at this area. More to do, more to play with. But what you would do is, if I had two air streams coming in and mixing, airstream 1, airstream 2, and I need to go out with 3, I would find the mass fraction for the things. So maybe this was 90% and 10%. Remember our mass fractions, the ratio of the mass flow rates of dry air? All right, I would plot 0.1 somewhere on my psychrometric chart. Oh, it's this dry bulb. I don't know, grab this point and this omega. There it is. And then, oh, where is state 2? Right there. And guess what you do? Oh, this is better than kindergarten. I draw a straight line. And then I measure the length of that straight line. And then I either go 10% from one end or 90% or whatever, you know. And so if it's if this fraction for 1, and this is state 1 down here, and this is state 2 over here, then it would be like right there. And you know what you just did? You did in omega, humidity ratio, and I know it's kind of funny, but you did it in terms of enthalpies as well. A lot of times people like axes that are perpendicular, but you can still have an axis that's not quite perpendicular, and that's kind of what we have. Is we have an enthalpy axis and a humidity ratio axis, and so the enthalpies are going like this. Think of only think going perpendicular, and so there it is. And then the omega axis is like this. So omegas go like this, and enthalpies go like this. And so you do interpolation on something that you would prefer it to be like this, and do the two straight lines. But it works with two straight lines in a fraction of the way. You can solve a lot of problems. I have 5 minutes. Maybe I'll give you a clicker question or two. Given this dry bulb, you're at 1 ATM, 30% relative humidity. What is the humidity ratio? And what's the best answer? All right. It's about right in here, isn't it? All right. So it's up. Okay, get rid of this out of the way. This is 0.0. What's this? This is 0.008. This right here is 0.009. So it's in between 0.009 and 0.01. All right. Good. Thank you for your attention. I'll have psychometric charts for you next time.